Deep within the Earth, there lie fragments of a former planet that collided with Earth eons ago, ultimately resulting in the formation of our Moon. During the 1980s, a remarkable revelation was made by geophysicists. They discovered two enormous blobs of unconventional material in the Earth's core. These blobs are each as vast as a continent, with one located beneath the African landmass and the other beneath the Pacific Ocean. It is believed that these blobs comprise elements in different ratios than the surrounding mantle and are about twice the size of the Moon. The origin of the peculiar formations, referred to as large low-velocity provinces, LLVPs, has long been a subject of inquiry. However, a recent investigation conducted by researchers from Caltech indicates that they may be remnants of a planet that collided with Earth during a catastrophic event that occurred billions of years ago. This event also resulted in the formation of our Moon. On November 1st, the journal Nature published a study that not only offers a solution to one mystery in planetary science, but also sheds light on another. For years, scientists have speculated that the Moon was formed when Earth collided with a smaller celestial body known as Theia. However, no evidence of Theia has ever been discovered in the asteroid belt or meteorites. The study proposes that a significant portion of Theia merged with the early Earth, creating the LLVPs. Meanwhile, leftover debris from the collision came together to form the Moon. Tian Yuan, the OK Earl Postdoctoral Scholar Research Associate, led the research in collaboration with Paul Asimov and Michael Gurnis. Asimov, a professor of geology and geochemistry, holds the Eleanor and John R. Macmillan Chair, while Gurnis is the John E. and Hazel S. Smits Professor of Geophysics and Clarence R. Allen Leadership Chair. Moreover, Gurnis is the director of Caltech's Seismological Laboratory and the Schmidt Academy for Software Engineering at Caltech. The discovery of LLVPs was initially made by scientists who studied seismic waves that passed through the Earth. These waves travel at varying speeds through different materials, and in the 1980s it was discovered that there were significant three-dimensional variations in the Earth's structure. The deepest part of the mantle displays seismic waves that are characterized by the signatures of two large structures located near the Earth's core. These structures are believed to have a high concentration of iron, which makes them denser than their surroundings. As a result, seismic waves passing through them move more slowly, and they have been given the name large low-velocity provinces. In 2019, as Yuan listened to a seminar on planetary formation given by Mikhail Zolotov, a professor from Arizona State University, he noted something interesting. Yuan, who is a trained geophysicist, observed that the Moon holds a substantial amount of iron in comparison to other celestial bodies. Zolotov introduced the giant impact hypothesis, but he also mentioned that there was no evidence of the impactor that had crashed into Earth. According to Yuan, as soon as Mikhail mentioned the elusiveness of the impactor's location, she experienced a sudden realization, often referred to as a eureka moment, that the impactor, which was rich in iron, could have undergone a transformation into mantle blobs. Yuan collaborated with a diverse team of specialists to create models depicting various scenarios involving Theia's chemical structure and its collision with Earth. The simulations verified that the collision's physical forces could have given rise to both the Moon and LLVPs. Portions of Theia's mantle might have merged with the Earth's mantle, where they later conglomerated and solidified, resulting in the two evident masses present today at the Earth's core mantle boundary. Other fragments resulting from the impact fused together to create the Moon. How did Theia's material form into two distinct blobs instead of blending with the rest of the developing planet, despite the violent collision? The researchers' experiments showed that much of the energy delivered by Theia's impact remained in the mantle's upper half, leaving the lower mantle at a cooler temperature than previous lower-resolution impact models had estimated. Because the lower mantle didn't completely melt, the blobs of iron-rich material from Theia remained mostly intact as they sank down to the base of the mantle. This occurrence is akin to the solid masses of paraffin wax in a dormant lava lamp. If the lower mantle had been hotter, it would have mixed more thoroughly with the iron-rich material, much like the colours in a stirred pot of paints. The following course of action involves analysing the potential effects of Thayer's assorted substances on the Earth's internal mechanisms during its early stages. Specifically, this examination aims to shed light on the influence it may have had on the planet's plate tectonics. According to Asimov, it is a rational conclusion to draw that the LLVPs are remnants of Thayer, which would mean that they are incredibly old. Therefore, the next logical step would be to examine the impact they had on the earliest stages of Earth's development. This includes investigating the initiation of subduction before optimal conditions for contemporary plate tectonics existed, the creation of the original continents, and the genesis of the oldest remaining terrestrial minerals. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.